That's all I get today, I think. But you said that no one does bits anymore, right?
Nobody does bits. It's
I get
cash for
Just donuts.
Just donuts.
Donuts. Thanks for the donut. That's what you say, right? Or thanks for the gifted subs.
Yeah.
Okay, so while we're at it, I know we got cut short yesterday. D, let's finish D from the previous problem and we'll discuss it. So hopefully you figured that out. And this is the big idea. And so if you combine this, with the fact that that's true, right? And so you go, okay, well, my final omega. So assuming I go from rest and accelerate up to some. It's kind of like an uwu, isn't it? It's scary. Anyway, so you'd have, well, okay, what's the relationship? Well, starting at 0, omega would just be alpha times t, right? And so, well, what if instead of writing alpha, because this question D is asking, what's the relationship between time and like some desired final frequency? Well, replace the omega with 2 pi f, right? And what do you replace the alpha with?
E over
Tau over I. Yeah. And the question's asking, how long does this take? So I'm solving for time, and so your answer would be like 2 pi f times I divided by the torque, which hopefully makes sense. I mean, look at that equation. That says, what does increasing the torque do to the time it takes? Makes it less bigglier. How about increasing the desired frequency? If you're like, I want to get this thing spinning at 500 rotations per second versus 200, well, it's going to take more time. And what does increasing I do? If you make the thing more massive or bigger, it takes more time as well. Make sense?
Yeah.
Okay, so, and of course you could write this, you could replace the I with mr squared if you want. This is, I think I touched on this yesterday. If you wanted the final answer to just be in terms of the mass, the radius, the frequency, and the torque, you have just replace the I with mr squared. Okay, 13. Who got an answer that they're confident in? Aaron, what'd you get for I?
I got 60 pi.
60 pi? Go back. What'd you get? Different answer? Or anyone else? No one else? Okay, well, let's look at no one else even got like an answer?
65.
You got 65? Yeah. Okay, let's just look at the math here. So you go, what information do we know? We know the radius is 2. So the radius, so if you're just listing out all the info given, then they give us the radius. They give us a time, 8 seconds. They give us an initial frequency and a final frequency. What's the initial frequency?
0.
From rest, so 0. So that means the initial omega is 0, which means, and the final frequency is 12. So what's the final omega? 24 pi, right? Because each rotation has 2 pi radians, or you're just looking at this formula. Okay. And so if you just write the famous formula, torque equals I alpha. I suppose in this one, I guess you could just use this derived formula, but let's look at how it looks if you just, if you go from starting from like first basic principles here. You'd write the famous Newton's law. You'd say, it says how much torque, so I'm solving for the torque. The I value is m times r squared. And so the mass was, I forgot to write that down, it was 5. The radius is 2. And the alpha desired is 3 pi, right? So 24 pi is the change in omega divided by the time that took. So you have 3 pi times 4 times 5, which of course is 6 pi. Units?
Newton meters?
Newton meters. Not super obvious. This is the beauty of SI units. Is if you're like, well, wait a second, my units are kilograms multiplied by meters squared multiplied by radians per second squared. So if you think about that, that does come out to be newtons times meters. Because you have kilograms times meters per second squared multiplied by meters, where the kilograms times meters per second squared is a newton. Okie dokie. All right, I hope that all makes sense. I want to say, I mean, these should be hopefully fairly straightforward. Maybe some quick remarks on like, so when you look at like this, say you write it like, so for a single mass on a rod, it's the I is mr squared. Okay. So what happens to this? So suppose you're always exerting the same torque. So say you have like a motor that always exerts the same amount of torque. What happens to this if you like double the mass?
It's twice as big. Right?
Get half as big. Unless I said it wrong. If you double the mass, if this is staying the same and you're doubling the mass, that would cut that in half.
Yeah.
That'd be like, I got this motor. I'm gonna use the motor to drive this flywheel or something. Well, if you make the flywheel more massive, it's gonna decrease the acceleration you get. What if you double the radius?
It's 4 times as small.
You get 4 times smaller. Okay. Last little thing. Well, let's cover 2 more little things. And I want to have some work time here. Let's give us a nice head start. By the way, we're going to end. So next week is the last week, so we'll have a quiz on Friday. We'll have. I think it's a nice coincidence, not coincidence, I guess, but we're going to have plenty of time to like. We won't have to rush it all to finish it. So. Let's look at 18 together. So. Sometimes they'll just give you the I value of something. Like it could be anything can spin, right? It could be this weird object, and you can, oh, this thing's gonna. If you put this on an axle, for example, and wanted to like exert a torque on it to spin it, you would want to look at like, well, what's the I value of this thing? How do I calculate the I value? So that's kind of like number. You'll see when you do number 17. You're not going to actually calculate the I value. You're just being told that I value is I, so then work with that. But on 18, I'm going to show you how to calculate the I value of this weird structure here. And then we're going to show how do you calculate the I value of like a solid ring. And then from there, I'm just going to give you the rest. So there's I values for like a sphere, like a solid sphere, a hollow sphere, hollow cylinder, solid cylinder, really anything you can think of. So, okay. Is this making any sense, or why there'd be an I value for like any object that can rotate? All right, let's look at 18. So this is not the whole story. This would be for millions, zillion dollars. What do you think the formula is if you've got not just one little point mass in your system, but many point masses? What symbol can you throw into the equation that makes it make sense? It's for $1 million. For $1 billion.
Delta? No. I was thinking about one.
I knew you won't guess.
Yeah, that one.
Sigma.
We
We've talked about sigma.
I was gonna say.
Well, that was the 100% guess.
What does sigma mean?
AutoSum.
What? Anyone know what sigma means?
Oh, yeah.
Sum. Sigma means sum. This symbol means if you've got a bunch of masses, right? Huh?
Like an Excel.
Yeah.
Yeah,
That's what I
exactly. Yeah, if you have a bunch of items and you want to talk about adding them up, that's what this symbol usually denotes, is like you're adding up a whole bunch of terms. So if you got a whole bunch of point masses, each mass has a mass and an associated radius value, so you just calculate them all separately and add them all up. So for 18, let's calculate it. Weird structure here. Okay, let's deal with the inner guys first. How massive is each one? 5 kilograms. Okay, all 4 of those are 5 kilograms. And what's their R value for each one?
3.
3. Everyone's okay with that? So let's calculate that. These guys, their contribution to the I value would be mass times R squared plus mass. So that's the first one. And the second one is mass times R squared. And then there's the third one, mass times R squared. And there's the fourth one, mass times R squared. Okay? You feel okay about that? Yes, Andy?
There's not a shorthand version of that.
What do you think?
Take the one times the back line.
Multiplication. Multiplication. You could say 5 times 9 square times 4. Okay, so then how about the outer guys? These guys are at a radius of 6 meters and they have the same mass. So those guys would contribute 5 times 6 squared plus 5 times 6 squared. I'm just writing out this one time because I want to show you that's what's technically sigma means sum, but we are, we know a little bit of math, so we can say, well, yeah, that's just, that right there is just 4 times 5 times 3 squared. And this guy here is 4 times 5 times 6 squared. So what do we get here? It's worth looking at what they each contribute to the system. So what this guy's contributing, 45 times 4, so 180.
Yep.
This guy contributes 36 times 5, so 180 times 4, 720.
Yeah.
I think that's right. You can check. Fact check me. So the total is 900. 900 what? Inertias. Think of the units. Each of these terms has the units of kilograms multiplied by meters squared. You feel okay about that?
Yeah.
Sadly, there's no fancy unit for that. Do we feel okay about that? Okay. Part B says, let's suppose we apply a 450 Newton force tangentially on the outer ring over an interval of 8 seconds. And then we're answering 2 questions. What will be the angular acceleration of the system? Let's do that one first. So now we're going to go here and go somewhere on the rim and exert force of 450. What do you think we're going to turn that 450, the force into?
Angular acceleration.
Torque.
Torque.
Okay.
That's what I was.
So what you're going to do is say, well, if you exert a 450 Newton force on the outer ring, how much torque is that on the system? Let's calculate the torque. Who remembers the definition of torque?
I times, what is it?
No.
It's mg times that.
Oh, remember, generally speaking, if you've got a radius and you exert a force,
Oh.
the torque is the force multiplied by the radius. Okay? So the more force you exert, the more torque you exert. The farther away from the center of rotation you exert the force, the more torque there is. More twisties. Okay, so the torque is force times radius. So what does that come out to be? The force is 450. And the radius is 6.
Oh,
Is that
okay, so you don't add both the inner and the outer radius together, that would have been
2700.
well? So the question so this definition, R means the distance from the center of rotation to where the force is being applied. So just because this is 3, that doesn't really mean anything. I mean, this is 3, but this whole thing is 6.
Oh,
This is the problem told us is that the outer radius is 6.
okay.
Make sense?
Mhm.
So that's 2,700
Yeah, yeah.
units of torque,
Newton meters.
Newton meters. Okay. We're halfway there. We got the torque. Are there any questions on that torque calculation? You feel okay about that? Okay, then what's the how are we going to get the angular acceleration?
I times alpha.
You go torque equals I times alpha. We know this. Just calculated it, 2,700. We know the I value. And so we know alpha is 3. 3 what? Radians per second squared. Does everyone feel okay about that?
So that I is just all combined points.
Yeah, I is the sum of all, what happens if you sum up all the contributions to the m in the r squared? Here's a question for you, Aaron. Actually, not just for Aaron. Why do you guys, what do you guys think is the smooth version of this? This is discrete, right? There were 8 dots. So if you want to add up 8 discrete items, it's called sigma. What if you had like a solid object and you had to like just smoothly add up a whole bunch of space, a whole bunch of density? Integral, yeah, for you quackalus people. It's called an integral. Good. What? Sometimes I. Okay, so if that's the alpha, then what's the final speed then? What's the final angular speed or angular velocity? Well, hopefully this one rings a bell, or I mean, not like you have to do it this way. You might just go, well, I know that it's starting at rest, so 3 multiplied by the time. So what's the answer? And the time is 8 seconds, so. Here's a question for you. Roughly, how many spinnies per second is that?
12 pi. Or no, 12 over pi.
Yes. I was going to say about 4, yeah.
Oh,
Because there's roughly 6 radians in a rotation. So it's going to be just under 4, but you're totally correct. It would be 12 divided by 5. Okay. Let's cover one last thing, because then we'll be a little ahead of the game. And then next week we can have some more work days. we're gonna look at 20 together. So 19 hopefully is straightforward for you. Hopefully not too mysterious. Sorry. Anyway, why don't you try to answer A? It's not super duper easy or anything, but I think it's doable. So you got, so each little ball is a mass of little m. And so you can write an expression for the total I, how those contribute to I, and then think about, well, what's the total mass of the ring? Can I write a formula? Mr. Trenton, you're not trying. Trenton, use your patriotism, bro.
We're
I
trying.
wanted you to try 20A.
Okay. I can do that.
I'll try about 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 18, 19. Got one more, 20. Okay, good enough. Close enough for government work, as Michael J. Knudsen would say. Did anyone get it? Did anyone get an answer for what's the rotational inertia in terms of the total mass m in R? Close. Okay, you're getting there. So this is R, right? So the
I know. That looks good.
did everyone get that? You get the so you have the sum of all the masses times the R squares, right? So you're like, well, they're all the same radius, so there's 20 of them. So I'd say 20, and be really specific about this, like little m times radius squared. But wait a second, what's this number mean?
Big M.
That's big M. That's the total mass of the ring, right? Make sense?
It's really that simple.
Yeah. So this is a bigly idea, actually. You got to really think about this one. What this tells you is that, so remember how like one point mass, what's the I value for a single point mass? mR squared. Well, what's the I value for a whole bunch of point masses that have the same radius? Just mR squared, but m is the total mass. So you can think of this as being almost like a single point mass distributed over a whole ring. Does that make sense?
Yeah.
Okay, and then if you exert a torque on the object, what will be the angular acceleration?
Let's calculate that.
I actually have a question.
Yeah.
What happens if the mass is unevenly spaced around the string? Like with the,
You'd still have the same I value.
usually not symmetrical. Yeah, yeah.
Right. As far as like, how would that, I actually have a little setup. I'll show it to you on Monday, a little thing. So like, if you have more of the mass here, then it's going to want to sit. Its equilibrium is going to be like having most of the mass sit low. So when you go to drive that, it's going to be like not so well behaved. It's going to be, I want to say wobble, but when you rotate it, it's going to exert some torques on the motor. So Does that make some
Yeah.
sense? Okay, so what's the angular acceleration? The torque that they're just saying is tau, okay, that's the torque, and then divided by the I value, which is this, so kind of a familiar result, right? Make sense? And then how about the linear acceleration of one of these points? Say you wanted to look at, say, oh, that'll tell me how many radians per second squared the system is accelerating, but what if I wanted to know how many meters per second squared one of these guys? What's the relationship I want to use? Very good. A equals alpha times R. So just multiply that alpha by R. What would come out? We all feel good about that? That's the part. Huh? It's the same R, but yeah, it's good to make sure you're being vigilant about which R is which and all that good stuff. And then C says, make a conjecture about the formula for the moment of inertia for a solid ring. Well, what if it was 50 little point masses? You have 50 there, it's the same idea. What if it was 1,000,000, right? So that's what a solid ring is. It's just this idea, you expand it out to 1,000,000 little point masses, and that would be like a solid ring. So for C, the answer would just be that make sense? Yeah. So if this is a solid ring, then the I value is just the total mass of the ring times the square of the radius. And so anyway, and Colin, back to your question, it's an interesting question because I believe the I value, if it's a ring, so if this ring was say of different densities, so say this is iron, and this is steel, and this is aluminum or something, you should still be able to use the same argument, I think. But what would be interesting is that then you start talking about like a disc or like a ball or a cylinder of say like a cylinder where the core of it's more dense than the outside, then it gets really complicated. There's actually I'll show it to you guys next week. There's a Wikipedia page that lists, someone has gone and listed out like all the moments of inertia for like any kind of object you could imagine. It's like tetrahedrons, rectangular prisms. That is a surprisingly complicated formula. Rectangular prisms, you get the idea. It's all sorts of crazy shapes. Okay, and then so for D, look at D. What? Well, for D, it says this one, in order to prove this is true, you got to use calculus, and so this is calculus class. That's okay. I'm going to give you all the other famous ones eventually. This is one famous one. If you had a solid disk, it turns out, so a solid disk where the total mass is m and the radius is r. It turns out that the I value for a solid disk is half of m r squared. So, well, what's up?
You probably answered my question.
First thing that's interesting is, well, what does that mean? Like, what is easier to spin? What spins more easily? A ring, a solid ring of some mass and radius squared, or say you distribute that mass over a disk of the same mass and the same radius. Which one's easier to spin? Right? Well, look at the formula. Oh, okay, it's okay. We're just getting used to it, right? What's true? When you exert a torque on something, right? The bigger the I value, the smaller the acceleration you're going to get. Right? Make sense? So for example, what's something that has a small, something with a small I value, maybe be like an aluminum flywheel. Something really light, spins really easily. Whereas a big, huge steel disc, right, has a big I value. That's not going to accelerate as much when you exert a torque on it. Does that make sense?
Yeah.
So what I'm trying to get at is this guy, for a given mass and radius, if all the mass is out at the maximum radius, if it's all out here at this radius r, then the I value is bigger. It's harder to rotate than if you have it distributed throughout many different radii. Does that make sense? So the idea, so you just have to make a little explanation that I just want you to make one that makes sense to you. For example, if I go back to the point mass idea, if I imagine a whole bunch of little point masses all over this thing, well, right, what's true for a lot of these point masses? You got small radius. Make sense? A lot of the mass is very close to the center of rotation. So when you're doing this, mr squared thing, well, all the masses that are very close to the center don't contribute very much to the overall inertia. So last thing I guess would be what's gonna have a bigger I value if you had, so say you made a disk and you went, so same mass. What if you made this part, this would be iron. If you went iron and then aluminum on the outside, versus what if you went aluminum on the inside and iron on the outside? Which one has a bigger I value? The one that has its mass, it's more massive substance, it's denser substance, like farther away for bigger R values. Okay. Thanks for the donuts. Hey, Trenton.
Yeah.